Okay guys, in this video I wanted to illustrate one more type of problem involving weak acids and weak bases. In this problem we are going to be given the Ka for a weak acid, and what we'll be asked to do is to determine the equilibrium concentrations of all of the species. Okay, so in the previous problems they gave us the pH, for example, and we used the pH to figure out what the hydronium concentration was. In this type of problem, all we're going to be given is Ka and the initial concentration of the acid, and then we need to find all of these equilibrium concentrations here. Okay, so we've got our weak acid ionization, we've got the ice table, we know Ca, we know the initial concentration of the acid, and we know Ka, but we don't know anything else. So what we do is we set up the Ka expression for the ionization, for the acid ionization reaction. It's the hydronium concentration times the conjugate base concentration divided by the acid concentration, and then we substitute in the equilibrium, the symbolic equilibrium concentrations. So that's going to give us x times x, which is x squared, divided by Ca minus x. And now this expression here, coupled with the Ka value, in principle it can be solved using the quadratic equation to find the value of x. And so here is what I've done here is I've taken the expression here and rearranged the equation in the quadratic form, and then you use the quadratic formula to find the value of x. And so x is equivalent to the hydronium concentration, and so you can use the value of x to calculate the pH of the solution, for example, or you could use the value of x to calculate the percent ionization, just like we did in the previous video. In many cases, however, the acid is so weak, that is, the value of x is so small that you can neglect minus x relative to Ca. That is, x is insignificant compared to the value of the acid's initial concentration. And so if you can make that approximation, then the problem really simplifies a lot. You ignore the minus x, and that just gives you Ka equals x squared over Ca, which is much easier to solve. X will be approximately the square root of Ka times Ca. And that's a lot easier than dealing with the quadratic formula. So you want to use this approximation whenever you can. The question is when is this approximation valid and when is it not? Well, a test you can run to see if you can use the approximation is to take the value of Ca, divide it by the value of Ka, and if the result is greater than 100, then you can be pretty confident that this approximation is going to work. However, if Ca divided by Ka is less than 100, then you're pretty sure that the approximation won't work, and you're going to have to deal with the quadratic equation. And so we'll see examples of both in the problems that are coming. So in this problem, we're looking at a weak acid, formic acid, which is the irritant in ant's venom that makes the ant bite sting. It's a weak acid, so it donates a proton to water. That produces hydronium and leaves behind the formate ion. And here's its Ka value. Given the initial concentration and the Ka value, they want us to find the hydronium ion concentration at equilibrium and then use that to calculate the pH of the formic acid solution. So I've taken the acid ionization equilibrium constant expression, the Ka expression, substitute in x and x for hydronium and formate, and divide that by the equilibrium concentration of the formic acid. And so that gives us this expression here. Before we go about solving the quadratic equation, it's useful to test to see if we can make an approximation. That'll simplify the problem considerably. So we'll take the initial concentration of the acid, divide that by Ka, and we find that the value is approximately 3,000 in this case, which is greater than 100, So that means that we can neglect minus x relative to Ca, and we have this equation that's much simpler to solve for x. So using this rightmost expression equal to Ka, we then solve for x, which is our hydronium concentration. So substitute in Ka, substitute in the initial concentration of the acid, take the square root, and we get the hydronium concentration. Then we can take the hydronium concentration, like we've done in previous videos, substitute that into the pH equation, and that gives us a pH of 2.01 in this case. This problem is very similar, but instead of finding the pH of the solution, what we're going to do is find the percent ionization. So here we're looking at acetic acid again. Acetic acid donates a proton to water. That gives us hydronium and leaves behind acetate. The Ka value is given to us, and we have the initial concentration of the acid. We set up the Ka expression using the equilibrium line from the ICE table. Test whether or not we can use our approximation. We find that the ratio of the acid concentration to the Ka value is about 5,600, which is certainly greater than 100. And so we can neglect the minus x in the denominator relative to Ca. So that gives us the simplified equation, which we can then solve for x to find the value, the amount of acid that dissociates. And then we take that value of x, we plug it into our percent ionization formula that we looked at in the previous video, and that gives us a percent ionization of about 1.3%. So 1.3% of the acetic acid is in its ionized form. This problem here is illustrating that the same approach works for basic solutions. So here we're being asked to find the hydroxide ion concentration and the pH of a trimethylamine solution, where the initial concentration of the base is 0.25. So trimethylamine is a weak base. It accepts a proton from water, forming the conjugate acid and leaving behind hydroxide. We set up the ICE table using the initial concentration of the base. Here's the change in the concentrations and the equilibrium concentrations. We set up the Kb expression. Kb equals the product concentrations divided by the concentration of the base at equilibrium. And so that'll be x times x over Cb minus x. Again, we can check to see if we can use an approximation to simplify the Kb expression. We take the initial concentration of the base, divide it by Kb. We find that it has a value of around 3,300, which is greater than 100. So we can neglect minus x relative to Cb. That gives us this. We can then solve this for x. We see that x is equal to the hydroxide concentration. So substituting in the values of Kb and Cb, we get the value of the hydroxide ion concentration. And then we can use that to calculate the pOH. We get a value of 2.37. However, since this problem wants the pH, we need to convert our pOH to a pH by taking 14 minus the pOH to give us a pH of 11.63. This problem here is very similar to the one that we looked at before, where we calculated the percent ionization of an acid. Here we're calculating the percent ionization of a base. And so it's solved in exactly the same way, but instead of calculating the pOH, once we find our value of x, we substitute that into the percent ionization formula, and that gives us the percent ionization of the base. So in this problem, we were looking at the percent ionization of ammonia, and we see that 2.33% of the ammonia dissociates to form the ions. In this problem, this is an example of where the approximation that we've been using fails. So we're looking at the hydrogen sulfate ion, which is actually a fairly strong acid. It's certainly not a strong acid, but it is stronger than most. And so here's the acid ionization reaction. Hydrogen sulfate donates a proton to water that forms hydronium and leaves behind sulfate. Set up the ice table for this reaction. Set up the Ka expression. And then what we want to do is test to see whether or not we have to use the quadratic equation or whether we can use our approximation. In this case, the acid concentration divided by this rather large value of Ka gives us a value of about 4, which is in fact less than 100. Therefore, we would expect the approximation to fail. And so we cannot neglect minus x relative to Ca, and we're forced to use the quadratic equation to find the value of x. And here's the result. This is the hydronium concentration, right? X equals the hydronium concentration. Once you substitute in the numbers here, you would get this value for the hydronium, and then you can put that into the pH equation to give you a pH of 1.72. Here's an example of a base ionization reaction, this one for caffeine, where because Kb is larger, you really can't get away with using the quadratic equation. So I'll leave this one as an exercise for you to look at. And we'll stop the video here.